Okay, CJ,
Yes.
over to you.
Can you see my screen, Fiona?
Yes, I can. There we go.
Thank you very much. Fiona, thank you very much for the kind introduction. Hello, everyone. This webinar is focusing on electromagnetic simulations using FEKO for the defense industry. As Fiona said, my name is CJ Reddy. I'm the Vice President of Business Development for Electromagnetics in Americas with Altair Engineering. The agenda for today's webinar would be, we briefly introduce the CEM technology, the computational electromagnetic technology, and then we'll also see how the solutions scale for an example case of fighter aircraft. That is various solution technologies that we have, how they scale as we go to various frequencies from low frequency to very high frequency. Then we'll see a range of case studies that are mostly applicable to the defense industry and conclude the webinar maybe 10 minutes before 10 to 10. So we have some time for question and answers. So let's look at the CEM technology, and typically in the real life we have various platforms or objects like these ones, like aircrafts and ground vehicles and helicopters, and we would like to use a CEM tool that applies Maxwell's equations to get the electric and magnetic fields, and by getting them we can also get the radiation patterns, near fields and input impedances, all the quantities we would like to see in an electromagnetic problem. So to do this, of course one can use FEKO, which is a state-of-the-art CEM tool, and the FEKO widely been used for radiation problems, scattering problems, waveguide problems, as well as for antenna designs, antenna placement, micro devices, and bioelectromagnetics. It's now worldwide known tool with state-of-the-art technology incorporated into FEKO. So let's look at various problem space that we have. That is, if you look at the complexity of materials and the electrical size, it varies from one extreme, the human body with lots of materials in there that need to be modeled accurately, and the other side, large electrical size of the platforms like ships, for example, that can get electrically very, very large as you go to higher frequencies. So to solve these things, FEKO has various methodologies. One of them, the base methodology, is meter moments, and then we also have finite element method, finite difference time domain method, MLFMM, multi-level fast multipole method, and physical optics and geometrical optics, and UTD. So these methods, FTTD, FEM, meter moments, MLFMM, can be termed as full wave methods. That means they can give you very accurate answers if your CAD model is correct and your meshing is done right for those problems. Of course, they can be applied to any frequencies, but you'll notice that these methods will run out of memory and CPU time at some point in the electrical size. That's why we have this various staircasing of these methods that are applicable to various electrical sizes. So once you reach the maximum memory limit for MLFMM, one can also use physical optics and geometrical optics and uniform theory of diffraction, which are the asymptotic methods with approximations that can be applied to electrically large structures. FEKO incorporates all these techniques, but also hybridizes them. You can see that various methods that are hybridized with each other. So in each problem, one can use full wave method for the part of the problem, and for the rest of the problem, one can use the asymptotic methods. This makes FEKO the most powerful tool for electromagnetic analysis, and also very flexible tool. So you're not restricted by, can I use only this method, and restricted by the size of the problem or the complexity of the materials in the problem. You should be able to do both using various technologies that we have in FEKO. So just to give you a brief introduction to the graphical interface that we have, there are two main parts in the graphical interface. That's CADFEKO and post-FEKO. CADFEKO, which is shown here, incorporates various tools that to create the CAD models, and also import the CAD models, import the meshes, various meshes in various formats, but also set the simulation, set the excitations, frequencies, and also request the output parameters like radiation patterns, RCS, and other kind of outputs in there. So very user-friendly, and it's a state-of-the-art graphical interface that users can learn very quickly and start using it very quickly. Then we have, of course, once you set up the problem, you solve using FEKO solution, and then we have what's called post-FEKO, which is used for visualization of the results that you get, the radiation pattern, input impedances, etc. Both post-FEKO and CADFEKO, CADFEKO also comes with the importation of the other CAD formats like IGES, ACES, and all sorts of things that you can import into CADFEKO. Both CADFEKO and post-FEKO come with a Lua scripting, so you can create your own scripting so that you can create your own models and your own processes within these two tools. Very powerful graphical interface, both for the CAD creation and CAD repair, as well as the setting up the problem and visualization of the data after the problem. So let's look at the solution scaling. Now that we have all these methodologies in FEKO, how do they scale with the electrical size of the problem? So for the solution scaling, we picked a representative fighter aircraft here, and which you can see that whatever may be the size of the aircraft here, you can see that the length and wingspan are represented in electrical length, because this is the critical thing that that creates the memory requirement for the problem to be solved. The larger the electrical size, the more memory is required. So that's how we went from very low frequency, where the electrical size of the aircraft is 10 wavelengths by 5 wavelengths maybe, and going all the way to 20 gigahertz, which is 1000 wavelengths by 533. How do we use various methodologies we have in FEKO to solve this problem? Let's say you put an antenna on the top of the fuselage, and you would like to solve this for a radiation problem. Let's look at method of moments, and very briefly, method of moments, you create a geometry, a CAD geometry, and you mesh with it surface triangles. So just to note is that method of moments creates a matrix equation, ZA equals V, where you solve for the current I, and that current, using that current, one can compute the near fields, radiation patterns, input impedances as parameters. So all you have to do in FEKO is create the CAD geometry and mesh it with the triangles, and ask to use method of moments as a solver, and you get the currents, as well as the with the currents you can also get near fields, radiation patterns, input impedances. So using method of moments, we tried this on a machine that has 32 gigabyte RAM. So you can see that 200 megahertz, it takes around 500 megabyte, 200 megahertz frequency, it takes around 500 megabytes of memory and 4 minutes of CPU time. So pushing this all the way to 600 megahertz, that is 30 wavelengths and 16 wavelengths in wingspan, it takes around 30 gigabytes and 9 hours of the time. This is where we can look at and say, what can we do before, after the going beyond 600 megahertz? So just briefly looking at the resource requirement, basically you have to invert the matrix here, the Z matrix here, which takes order of n cubed operations, and so order of n squared memory. This means that order of n cubed means if you solve a problem at one frequency at let's say one hour, it takes 64 hours to solve that same problem if you double the frequency. Same thing with the memory. If it takes 1 gigabyte for one frequency, and if you double the frequency, it takes 16 gigabytes. This is not a sustainable model when you keep on going electrically large structures. Of course, it is a very accurate method. Method of moments is very accurate and well documented and well trusted by various communities, EMI, EMC, antennas, and all those things. But at the same time, it suffers from this problem of memory scaling and CPU time scaling as you go to higher frequencies. That's where we introduced multi-level fast multipole method, which is like method of moments, but an enhancement of method of moments for electrically large structures. What does MLFMM bring to us to the table? You can see here that instead of 64 times the initial time and 16 times the initial memory, it only takes 6 times the time of the and then 5 times the memory. That means if you solve a problem at one frequency at 1 hour, it only takes 6 hours, not 64 hours, and also 5 gigabytes rather than 16 gigabytes of memory increase. So this is a sustainable model going to higher frequencies. So using this one, we took the same aircraft and then gone all the way from 600 megahertz to 3 gigahertz. Now you can see the current distribution on the aircraft, which seems very, very accurate as you go to higher frequencies. So 600 megahertz, where we stopped with metronome moments, it took around 30 gigabytes with metronome moments. Now you can see that it only took 1.3 gigabytes for the MLFMM, and also 20 minutes of the time as opposed to 9 hours. So now with this, using the same computer, now we can go all the way to 3 gigahertz with 145 wavelength long aircraft and 80 wavelength wingspan, 2.7 million unknowns. We only took 21 gigabytes of memory and 7 hours of the time. So again, here we hit a brick wall kind of thing in terms of memory. It's good that we went all the way from 600 to 3 gigahertz. So going beyond 3 gigahertz, what can we do? That's where the physical optics comes into picture. Physical optics works in a very simple principle that you compute the currents on the surface using this formula 2n cross h. N is the normal to the surface and h is the instant magnetic field. This is a very simple formulation, no need of forming a matrix, so there is no order of n cubed, order of n squared, time limitations or memory limitations on it. One of the good things, this method has been around for a while in the literature from 60s and 70s, when memory is a real problem than today. But one of the unique features in FEKO is that it has also been hybridized with metronome moments. That means your antenna, which could be very sensitive to the accuracy of the currents you compute, could be modeled using metronome moments, and the platform, which could be a smoother surface, can be modeled using physical optics. So both methods can exist in the same problem, giving you very accurate answers. So using physical optics, now going all the way from 3 gigahertz, let's look at 3 gigahertz, where we have solved the problem with the MLFMM. With physical optics, it takes only 570 megabytes of memory and 8 minutes of CPU time, as opposed to, if you remember, it took 21 gigabytes of memory for MLFMM and 7 hours for the CPU time. And now with this one, we can go all the way to 20 gigahertz in frequency with the same computer that we have, with 30 million triangles, 30 gigabytes of memory, and 20 hours of the time. Because the size now, we're talking about 1,000 wavelengths by 500 wavelengths size of the problem, which is very impressive considering that we use the same computer with a limited memory, 32 gigabytes, and could go from very low frequency using metronome moments, very accurate solutions, and also using MLFM, very accurate, and also using physical optics, which can give us reasonably good answers at higher frequencies. So this kind of shows the power of FEKO for this type of applications, going from electrically smaller objects to electrically very large objects, using not only the full wave solution but also the asymptotic solution and a combination of the both of these technologies. So going beyond physical optics, FEKO also provides a method called uniform theory of diffraction, where you don't need to discretize the object. You can model the object as a flat plates. That's one of the limitations on UTDs, that you have to model the object as flat plates. Once you model the object as a flat plates and can compute, and FEKO can compute all these mechanisms of UTD. What this means for us is that, as a computational cost, is that once you are able to solve the problem at one frequency, UTD can solve the same problem at higher frequency with the same amount of memory and same amount of CPU time as you go higher up in frequency. As an example, we took a ship. We approximated the ship to a flat plate model, as you can see here, and we placed a 25 by 25 array on the side of this mast here, and computed the radiation pattern at 1.77 gigahertz. And you can see that for such a, even though the frequencies seem to be lower compared to the fighter aircraft, ship is a larger structure, so electrically it is much larger at 1.77 gigahertz than the fighter aircraft. It would have resulted in a 32 million unknowns, which is very, I would say, if not impossible, if not, it is almost impossible with the memory and CPU time that we have. That means even if you have the memory of terabytes, it may take months to compute the radiation patterns on a shape like this, on a problem like this with 32 million unknowns. So instead we used UTD, and as you can see, UTD only took 8.4 megabytes of memory, which is nothing in today's world, and also took only a runtime of 18.4 seconds per angle. That means each angle is computed 18 seconds. So of course less angles are computed, it takes less time. More angles computed, it takes more time. And here we show the three-dimensional pattern of the array on the ship. And of course 2D pattern shows the red line is array in free space, and the blue line is the array on the ship, which you can see that there is another lobe that popped up because of the fact that we mounted the array on the ship. So it's important that we not only analyze these antennas and arrays on while designing on their own, but also the installed performance of these antennas on various platforms is very critical as well to know what's going to happen to the radiation pattern on these structures. With that said, so we have seen the power of FEKO applying from very small problems to electrically large problems. So let's look at some case studies. Some of them are done in the literature that we picked to showcase here, and some of them are our own benchmark problems that we have done. So let's look at it one by one. The first one is validation of FEKO model for a Boeing 707. This work was done by Saab in Europe, and they presented a paper at ICHIA 2012 conference in Cape Town, South Africa, in a paper called Validation of Computational Electromagnetic Model of Boeing 707 by comparison to scale model measurements. This is very critical because we can do computations, but at the same time it's good to validate using measurements. In this case, you cannot really do measurements on a 707 aircraft because it takes a huge chamber to put in a 707 and do the measurements. If you do, because it's also flying object, you cannot do it on a ground in an open range because the ground reflections will affect it. So normally people make a scale model of the bigger aircraft. In this case, it is scaled 1 to 25 scale, which means that if you're analyzing if you're looking at a 100 megahertz antenna on a full scale model, you should actually design an antenna for 2.5 gigahertz for the scale model measurements. That means the frequency goes up by 25 times because the electrical size has reduced, the physical size has reduced 25 times the full scale model. So one of the difficulties with the scale model is that if you have, let's say, a 10 gigahertz antenna on the aircraft full scale model, obviously you cannot go to 250 gigahertz to do the measurements. That would be a difficult problem to do. But it is very suitable for VHF, HF, VHF, UHF frequencies where measurements can still be done using the scale model. So some history from them given in the paper is that they have done in 1990 a basic scale model or kind of full scale models, I guess, using this type of, you can see on the left hand side a very crude model of the aircraft fuselage in open range. Again, when you do this in an open range like this, you have to be careful with the ground reflections and should be able to accommodate them in your measurements and remove them when you compute the radiation patterns. Or you could, they also did, looks like in the past, a cylinder with end caps with a scale model type of cylinder with end caps to represent the fuselage measurements. These are good, but at the same time may not represent the actual aircraft. So now I think in 2012, they have a full-scale model of 707, scale model of a 707 that's fabricated. You can see in the picture here that looks similar to, maybe this may be a painted version. This is an unpainted version that they can use for measurements. So they did this on a 500-meter ground reflection range. That is still an open range, but mounted on top of a plastic cylinder, PVC cylinder wrapped with absorbers so that there are no reflections from there. And they took a lot of patterns and compared with the FEKO simulations to make sure that the scale model measurements are accurate as well. So they created an exact model of the scale model they fabricated, and of course if they measured 496 megahertz, it resulted in close to 200,000 unknowns. It's important to make sure that the computation resources are also within the reach for these type of problems here. So they used MLFMM. In FEKO, we offer MLFMM in two flavors. One is CFIE, Combined Field Integral Equation, and EFIE, Electric Field Integral Equation. EFIE is pretty good for open surfaces. That means you have openings like windows and things like that, or flat plates and other kind of structures. But if you have a closed structure, like in this case, for example, if you look at the computation model here, there are no openings in the aircraft. There's only one antenna here, and of course all the windows are closed with the conductive surfaces. So if you have a model like this, we recommend that use a combined field integral equation. One of the advantages of combined field integral equation is that the solution time is reduced dramatically as opposed to EFIE. That is because of the fact that MLFMM uses an iterative solver, and when you use EFIE, MLFMM tend to take more iterations to solve as opposed to using CFIE, which you can see in this timings that they reported in their paper. MLFMM with CFIE took around 1 hour with 11 iterations, whereas MLFMM with EFIE, Electric Field Integral Equation, took around 14 hours with 500 plus iterations. So obviously it makes sense to use CFIE and solve the problem in 1 hour rather than waiting for 14 hours. Because you may get the same accuracy between the two methods, but just that it solves much faster using CFIE. And of course you can also go to physical optics, which if you just use physical optics, it is solved in 2.3 hours. You can also apply meta moments to the antenna and use the decoupled one. That means the physical optics currents don't affect the meta moments, and meta moments current don't affect physical optics current. It takes around 7 hours. If you do the coupling, it takes around 14 hours to do the problem. This also shows the flexibility of FEKO, that you can use different methodologies, and of course you can arrive at the same answers but with the different memory requirements as well as different time requirements. Can give you a validation of the simulations as well by using the different methods in the same problem. Now let's take a look at the comparison of the measured data with the simulations. This is of course in this plane, the azimuthal plane or yaw cut off the one with a depression of minus 2.5 and 5.0. That is the elevation depression. This is go a little bit lower with the 2.5 degrees and 5 degrees. You can see that the black line is the measured data, and the blue line is the green line is the FEKO simulated data. It's quite a good agreement between the two, and even including here, I guess, if you see the 5-degree depression, there are the back lobes here in the back side. FEKO seems to predict them quite nicely, which is a validation of how accurately FEKO can do the calculations. And also you go to the elevation pattern, that is a cut around the along the aircraft tail to nose. You can see again here, the black line is the measured data, and the blue line, the green line, is the simulated data using FEKO. Considering the measurement inaccuracies and other things, we can think that this is a pretty good agreement between FEKO and the measurements, which validates that. So now you can go using these validations. Now we can go and do a full-scale computations using FEKO, and so you can be certain that FEKO calculations are accurate enough to be used in the system calculations of various antennas for radiation patterns, cosine interference, etc. So speaking of cosine interference, FEKO also can do coupling calculations with various antennas. FEKO actually has a capability. If you have, let's say, 5 antennas that you want to compute, we can actually go ahead and compute 5 by 5 S matrix for the 5 antennas to show the coupling between all the 5 antennas. So in this case, we're just showing 2. The top one with a blade antenna for VHF frequencies, and the bottom one also the same type of blade for VHF communications. You can see that the S11, that is for the top antenna, seems to resonate around 348 megahertz for an overall band of 50 megahertz. And if you take the coupling, that is S21, that is from the second antenna to the first one or vice versa, you can see that it's much lower than minus 50 dB, which is pretty good for this case because they are much farther away, as well as one is on the top, one is on the bottom, which really gives a good isolation between those 2 antennas, which is required. Going to the second case study, which is antenna placement and rotor modulation for helicopters. This is actually a special problem for helicopters. That is, not only you have an antenna placement issue, but also you need to account for rotor modulation, because all of the helicopters have rotors, and antennas inevitably are placed under the rotors. Because the rotor rotates, it creates a modulation of the pattern which need to be taken into account. And we can see how FEKO addresses this issue very efficiently. Now, of course, you can do a brute force by taking each rotor position and computing the patterns of these things, but FEKO has a methodology where you can do this very efficiently. So one is a placement problem. That is, you want to place an antenna here, here, and here, and see what happens to the radiation pattern as well as the current distribution. We're already seen for the helicopter model, for the fighter aircraft, as well as for the ship, and also for the 707, the antenna placement can be done using FEKO, using different methodologies. Second problem is what happens when you place an antenna at the top of the fuselage of the helicopter and then have these rotors rotate with various angles. What happens to the modulation of the pattern? So if you take the first one, before going to that, let's look at the efficient technique that FEKO has, which is called numerical freeze function, NGF. If you remember in the meta moments we showed, it solves the problem using ZA equals to V, where you have to solve this equation for the whole problem. That means when you place the antenna here, you have this problem to solve, and you have this one, again you go ahead and solve, this problem again you go ahead and solve. That would take a lot of time, because every iteration you're going through, you're solving the whole problem again and again, whereas all you're doing here is you're not changing the geometry, you're just moving the antenna from one location to another location. So FEKO offers this technique called NGF, where you can store the matrix that you solve, use it for this, what we call a static part, that is the part that is not changing, in this case the whole helicopter, and only compute the dynamic part, in this case the monopole antenna that is moving from one location to the other location. So in the first location, for example, here, you compute the whole matrix and you solve the problem, but you store the static part in a file. I think you can choose this in FEKO as an option, and FEKO stores this in a file called .ngf, and will be reused when you move the antenna to the second location or third location. So this makes it very efficient calculation to do multiple antenna locations to find out what is the best location to place the antenna on the helicopter, for that matter for any platform. So that's a efficient tool that is being offered in FEKO, which to my knowledge is not offered in any other commercial electromagnetic simulation tool. So antenna placement study, you can see that the current distribution that's computed, that's varying, and also the radiation pattern depending on the location of the antenna that changes. So you can see that it can be done very easily using FEKO here. More interesting case is the rotor blade modulation. That is, if you have an antenna mounted here, in this case we chose a turnstile antenna, and if you go back here, so again here using the FEKO's efficient analysis using numerical Green's function, we can say all the problem here, including the antenna, except the rotor blades, can be a static part in the meta moments matrix, and the blades can be the dynamic part. So you can do an efficient calculation. So the first location of the blades, one can do the whole problem, but then store the static part in the file and reuse it for various rotation angles of the rotor blades. So we take the turnstile antenna at 350 megahertz. You can see that it gives a nice pattern when it is not on the helicopter, and it shows with a small ground plane around it. And now let's take a look at the patterns when you're not only placing on the aircraft but also rotating the rotor blades. So 0 degree rotation, that means in this position here when the antenna is placed on the front of the fuselage, you can see that it is no longer a nice round pattern that we have seen for the turnstile antenna there. It has the variations because of the geometry that is mounted on. Not only that, once you start rotating it, you can see that the pattern doesn't stay the same. It changes a little bit, and 30 degrees it changes a little bit more, and 45 degrees, 60 degrees, 75 degrees. And so you can see the cut. Now you can see it more clearly. The three angles, 0, 30, and 60. There is a little modulation of the pattern. What this means to us, of course, as an electromagnetic engineers, we can supply this information to the system designers so they can take into account when they do the communication systems or direction finding systems and any other avionics. They can account for this in their signal processor so that this won't affect. If they were not to know this one, this may turn into some kind of a noise and inaccuracies in their systems, which would cause problems if you assume that there are no changes in the radiation pattern due to rotor modulation. So that's not only that FEKO offers the calculation of rotor modulation, but also offers this technique or numerical Green's function, which can efficiently do these calculations with less CPU time. So again, this is another plane. You can see the both planes. There is a modulation of the pattern that's happening there. So what is the advantage here for FEKO using the numerical Green's function? You can see that in this case, static part took around 68,000 unknowns, and then the dynamic part only 10,000 unknowns. So first rotation angle, this is where we solved the whole problem. It took around 6 hours to solve, and for each rotation we only took 2 hours in increment. So a total of 36, without this FEKO NGF, we would have taken 36 hours. Now we only took 16 hours. So we got a factor of 2.5 speed up because of this. Now let's go to the another example, airborne radar that need to be solved. In many of the military applications, this is a problem that designing a good radar that can go with the aircraft. So in this case, you see the full aircraft here and front body. So typically the radomes are placed in the front nose of the aircraft, and this particular radome that we're considering here is the typically used for the weather radar application. That is, you have a slotted waveguide array in the front, and that need to be protected from the weather and other elements of the nature. So a radome is placed in front of it. So basically the function of the radome is to make sure that there's no degradation of the performance of slotted waveguide array when it is placed inside the radome. So we designed our own slotted array that can work at 9.4 gigahertz, and you can see the nice pattern of the slotted waveguide array at 9.4 gigahertz. And we also designed a radome based on the paper given here, published in IEEE Transactions on Antenna Center Propagation in 2009, with a glass composite and also paint. So FEKO offers what's called a thin dielectric approximation, so you don't waste a lot of resources trying to model this a very thin structure and having a lot of meshing elements that need to be used for memory and CPU time. So we can actually model this as a thin dielectric sheet with much less resources. And then we use the antenna as we took the radiation pattern of the antenna and derived the spherical modes that are given in FEKO and use them as a source for this problem here. So if you take the panel itself, the radome material, and compute at various incident angles, you can see that there's a pretty good, there's not much of a transmission loss. There's less than 1 dB transmission loss, all the way to 85 degrees or so. Obviously, when you're at the 90-degree angle, there is no transmission through the radome because you're going tangential to the radome. Now you can see here the transmission, the radiation pattern with without the radome and with radome, they tend to agree quite nicely, except of course the extreme angles, which we know that it's going to be a problem for any radome, not just for this radome. And here also the weather radars tend to scan the beam in both planes, and we also simulated that to show that we can use our simulation method to scan the beam to go from one angle to the other angle. And you can see that all of these things with radome, without radome, in the front lobe is a quite good agreement of FEKO simulations as opposed to FEKO simulations for both radome and without the radome. So moving on, we also can do a conformal antenna design on a missile. And for this case, we use the 12-element microstrip array that's conformal to the surface of the missile. And we use the FEM technique for that. And in FEKO, we offer FEM hybridized with MLFMM. So you can use FEM on the array here, but you can use MLFMM on the rest of the body. That will give you the flexibility of FEM for using for materials and also the power of MLFMM on the missile body. So you can see that we could compute with the missile and without the missile for the array and could successfully compute the radiation patterns of the missile. Now going to the next topic, which is radar cross-section here, which is a popular topic in the past for the defense applications, and even now I think it's critical to make sure that the defense articles are minimized with the radar cross-section. So FEKO offers the plane wave excitation, which can be used for computing the radar cross-section object. In this case, as a generic missile that shows the bistatic RCS of the missile in both planes, one plane here and another plane is here. So more interesting case study is with a composite structure of the aircraft. Nowadays, all the aircrafts are becoming composite. Aircraft skins are becoming composite material made with composite materials, which is very critical to account for when doing the analysis. You can't assume that they're all conducting and do a perfectly conducting structure for analysis. So FEKO offers a methodology where you can see the bottom of the slide here. You can actually put the orientation of the fibers in the composite structure that can be accounted as during the simulations. And in this case, we used a particular fiber and epoxy type and their materials, and using a plane wave that's incident from the nose, one can see the radar cross-section with the blue line that is a carbon fiber radar cross-section, and the red line is the metallic aircraft here. And also you can see the differences in currents between the metallic aircraft as well as the carbon fiber aircraft there. Same thing here with the incident angle from the top, coming from the top, and we can compute that as well. So that's one of the flexibility that FEKO also provides. That we can not only compute these structures with metallic metallic objects, but also with composite objects, carbon composites or other composite structures as well. Going to the EMC studies that are also important in defense industry. obviously lighting is one of the things that everyone considers when you're flying. In this case, why FEKO for lightning? Typically time domain codes are used for lightning. In this case, what we realize is if you use a time domain code, it will need too many time steps to solve the problem. And also, we need a very exceptional low noise floor when you do the lightning analysis, because lightning happens outside the aircraft body, and the fields inside may be extremely low, which need to be captured for the sake of analysis that we need to do. And also FEKO offers efficient cable bundle analysis, which can be used for coupling of the lightning currents into the cable bundles. And we do have time analysis capability in post-FEKO that can be used to represent the data back in time domain. By the way, FEKO also offers a finite difference time domain, which can be used for time domain analysis. But we do feel that for the low noise flow that we need, using the metronome moments will be a best option for this case. Here is an example of a fighter, kind of a typical aircraft that need to be tested for lightning. Normally what they do is that they have a port here where you need to inject the current and also ground on the other side. So essentially you're sending the lightning currents through the aircraft and then ground them here. And if you send 1 ampere through the aircraft and monitor the fields outside, obviously they are much higher, the green line here. Inside, in various locations, when you do the magnetic field and electric field, much lower, like minus 55 dB ampere per meter, as well as almost like 140 dB volts per meter, much lower than the outside fields here. So one needs to be able to capture these things very efficiently, and in this case, when you use a numerical method, there's a numerical noise that can prevent some of these fields to be captured. And you can see that FEKO is able to do that very reliably because of the fact that FEKO is also one of the few commercial tools that can use low frequency stabilization using the loop star basis functions that can give you this low frequency one. So we used 3 cables inside the aircraft to see how to do the cable coupling. FEKO can use this cable analysis tool that it has got inside FEKO to do various types of cables and cable routings, and also using schematics to add lumped elements and sources and all those things that can give you both radiation problems, but also you can combine the cables to create a cable bundle that can run through this. This is very useful for EMI, EMC, not only for lightning case, but also for HRF and other kind of structures as well. We use the technology that we have in FEKO as a built-in package here for cable analysis to do this lightning coupling into the cables. And you can see that if we use initially a bare cable, that is, it's not shielded at all. You can see the cable type here is just a perfect conductor wire that's running around. Just to show that what happens if you do unshielded cable, you can see that the currents can go all the way up to 1400 milliamperes. But if you use shielding, which is also available in FEKO to use a shielded cable, you can see that the coupling of the current has come down to 21 milliamperes, which is a huge reduction. Because that's, one can say that we can do the shielding to reduce the EMI, EMC all the time, but the question would be, how much is the too much shielding before it increases the weight and cost that comes with the shielding of the cables. Before we close this one, and before we close the webinar, let's look at a couple of other case studies that are done. We thought very interesting for the defense industry. One is a helicopter FM antenna design. Typically, if you were to do a 30 megahertz to 88 megahertz, there's a long whip antenna that is used, which could be more than a meter or so in length. So instead, one can integrate, one can design a glass integrated antenna on the side of the helicopter, in the windshield here, the window here, and that could be used for the FM radio 30 megahertz to 88 megahertz for voice and data communications. So in this case, in this paper, that was published in IEEE Transactions in Antennas and Propagation in 2012. They used a scale model like earlier aircraft case as well, and did the simulations using FEKO and measurements using the scale model. You can see that the dotted line, which is simulation, and the solid line, which is the measurement, seems to agree quite well for the reflection coefficient, for the gain from the front, and also the gain on the back. They're reasonably agreeing with each other, and also the cuts, the azimuthal cut here as well as the elevation cut here, they agree quite well. So they could validate the design with the measurements as well as with the simulations. The other one is calibration of direction finding arrays. Typically calibrations for the direction finding arrays are done. In this case, we have a helicopter with 5 antennas on the bottom. They're used for direction finding. That is the angle of arrival of the signal that is coming from a particular direction. This is done normally for a broadband frequencies using a technique called correlative vector direction finding, CVDF. And CVDF requires storing of the radiation patterns, or what they call the manifold, into a calibration table, and that be used when a signal, unknown signal comes. You correlate that signal with the stored manifold to know the angle of arrival. So the typical calibration table looks like this, which is actually comparing the angle of arrival with the actual angle, and the angle of arrival falls in the center line here, the blue line, and the rest of them fall on the other side. So if your angle of arrival and the correlation matches, then you can predict the angle of arrival. So left-hand side is the measured calibration table, right-hand side is the simulated calibration table, and you can see that there's a pretty good correlation between these two, which indicates that they may not have to do the calibration table at all frequencies using measurements. Probably they can use simulations to create the calibration table, saving a lot of time and money for the measurements. Last example that we have is typically when people place antennas on a platform, they want to know how much detail is too much detail, or how much detail is required for the accuracy to be retained, or the accuracy that is needed. In this case, also published in open literature, light multi-role vehicle is considered, and typically they need the near field calculation for the IED jamming type of application, but also they need the far field calculation for the communication between one LMV to the other LMV or other ground forces. In this study, what they have done is they took fenders, steps, rear view mirror, back elements, radiator holes, hinges, roof elements, windows, tires, and seat. If you have all of them in place as a baseline versus if you systematically remove some of them, what kind of accuracies you expect when you do your simulations. So this is a critical thing for us because we think we can remove the details, but how many details need to be removed before you can compromise the accuracy. So this is a nice study that shows at various frequencies they have done rooftop mounted antennas operating at all the 150, 300, and 600 megahertz, and of course they use metron moments and MLFM for the simulations. They found that the radiator holes are least important in the near field, but still result in differences up to 3.5 dB, which is significant in some cases because we need to have within 1 dB, then 3.5 dB becomes an issue. So we need to include all of them. And the roof elements result in differences much larger than 1 dB in zones of weak and high gain due to the proximity to the antennas. And also hinges, for example, they ensure the electrical connectivity between the door and the rest of the body. So if you remove them, that connectivity may be taken away. And so removing non-important details, the far-field performance could be predicted with sufficient accuracy, but knowing what are those non-important parts may be important, may be critical to do those calculations. You can see here at 600 megahertz on the right-hand side, there's a plot that shows various accuracies that is going from right to left and front back to front based on the near field calculations, based on the full simulation of with including all the details, as well as the one that is removing the hinges. Same thing with the fenders, full vehicle simulation with all the details, and the vehicle simulation where the fenders removed here at 600 megahertz. The bottom one shows at 150 megahertz some of the roof elements at different angles. So overall, I guess is what we can say is that FEKO is a very very powerful as well as very flexible tool. Powerful because of all the simulation tools we have, as well as flexible because these simulation tools allow you to do different type of calculations using different technologies, and also the same calculation using different technologies to validate with one another. So currently FEKO is widely used in the world and also in the defense industry for antenna design, antenna placement, EMC analysis, radar cross-section, but also for the human hazard due to the radiation, as well as the HERO, that is the hazards of the ordinances because of the electromagnetic radiation, hazards to the ordinances because of the electromagnetic radiation. And also providing the hybrid asymptotic methods in FEKO is a big plus, and to my knowledge, again, no other commercial tool offers such a tight integration of various methods in one package. And we continue to develop more methods and more utilities in FEKO to best meet the needs of the users that we have. With that, I conclude my talk. Thank you very much for your time. I think we may have a few minutes for questions, and I'm willing to answer any questions that you may have. Thank you very much.
Thanks, CJ. Thanks for that very interesting webinar and some interesting case studies covered there. We have one final poll question which we would like you to answer. Here we go. It's which application are you most interested in? I've just launched that now, so if you could answer that for us, please, we'd appreciate it. And if you can remember to, when you close the webinar, there'll be 2 survey questions, 2 very quick questions that we'd appreciate your answer to, which will help us to improve our webinars in the future. Okay, we have a couple of questions here. CJ, can you see those questions?
Not yet.
Not yet.
You can read me the question here, or maybe I can answer them.
Okay. There we go. You should have them now.
Yes, actually.
Okay.
Is it possible to simulate a lightning current which is distributed within a uniform area, or is it only possible to simulate lightning current along predefined line? I don't see any reason why you cannot do a distributed a lightning current which is distributed within the uniform area because FEKO is a generalized tool, so you can create any structure that you would like to create and then induce the lightning current. Because again, when you have a you want to distribute the current, of course you can define an impressed current that is distributed over the uniform area, so you should be able to do that as well. So I don't see any reason why it cannot be done, as it can be done. I have the second question here. When using the NGF, the numerical greens function for rotor modulation, do you need to create separate files for each rotation angles of the blades? No, actually you can do a Lua scripting in FEKO where you can create one file and then go through the scripting to say keep running this program and also changing the rotor blade angles and use the NGF file that's available. So you can do this all in one project. And also alternatively, FEKO also gives an option for multiple configurations. That is, you create one base configuration and you can have multiple configurations that are different from the original configuration. So in those multiple configurations, the second one you can say, use the NGF that's already done, so it can be read from the file and can be used. Those are the two questions I have here. Any more questions? We may have 1 more minute to answer them.
I think that's all, CJ.
Very good. Very good.
Okay, thank you so much. Thank you everyone for attending. Goodbye.